Welcome to this coding problem walkthrough. Today, we'll explore an intriguing problem titled Sum of Square Numbers from LeetCode. In this challenge, we'll determine whether a non-negative integer can be expressed as the sum of the squares of two integers. Let's dive in and break it down step by step. In this problem, we are tasked with determining whether a given non-negative integer, c, can be expressed as the sum of squares of two integers, a and b. Mathematically, this means we need to check if there exist integers a and b such that a(2 plus b squared equals c. The input is a single integer c, where c ranges from 0 to 2 to the power of 31 1, and the output is a Boolean value, true if such integers exist, and false otherwise. For instance, if c equals 5, we need to verify whether two integers a and b satisfy a(2 plus b squared equals 5. For the first example, when c equals 5, the output is true. This is because we can find two integers a equals 1 and b equals 2 such that their squares add up to 5. Specifically, 1(2 plus 2 squared equals 1 plus 4 equals 5. Therefore, it is possible to represent 5 as the sum of squares of two integers. On the other hand, if c equals 3, the output is false. In this case, there are no integers a and b such that their squares add up to 3. Hence, it is not possible to represent 3 as the sum of squares of two integers. Next, consider the case when c equals 0. Here, the output is true. This is because we can choose both a and b to be 0, and their squares will add up to 0. Specifically, 0(2 plus 0 squared equals 0. Similarly, for c equals 1, the output is also true. In this case, we can set a equals 0 and b equals 1, and their squares will add up to 1. That is, 0(2 plus 1 squared equals 0 plus 1 equals 1. This demonstrates that both 0 and 1 can be represented as the sum of squares of two integers. Finally, let's summarize the constraints and edge cases. The input c is always a non-negative integer, and it lies within the range 0 to 2 to the power of 31 1. When considering edge cases, if c equals 0, the output is true because 0(2 plus 0 squared equals 0. For very large values of c, such as those close to 2 to the power of 31 1, the algorithm needs to handle large numbers efficiently. Additionally, certain numbers like prime numbers, such as c equals 3 or c equals 7, may not have any valid solutions. On the other hand, perfect squares, like c equals 4, can often be expressed as the sum of squares, such as 2(2 plus 0 squared equals 4. These considerations highlight the need for both correctness and efficiency in our approach. To solve the problem of determining whether a non-negative integer c can be expressed as the sum of squares of two integers, we considered several approaches. First, the brute force approach. The intuition here is straightforward. Iterate through all possible values for a from 0 to the square root of c and calculate the corresponding value for b(2) as c a(2). Then, check if b is an integer by verifying if the square root of b(2) results in a whole number. While simple to implement, this method has a time complexity of approximately O(sqrt) c log c, as calculating the square root for each iteration adds additional computational cost. This approach is not optimal for larger values of c due to its repeated square root calculations. To address this inefficiency, we considered the optimized two-pointer approach. By leveraging two pointers, one starting at 0 and the other at the square root of c, we can systematically adjust the pointers based on the sum of their squares relative to c. If the sum is too small, we increment the first pointer to increase it. If the sum is too large, we decrement the second pointer to reduce it. This avoids redundant computations and reduces the complexity to O(sqrt) c, as each pointer only moves a limited number of steps. This makes it significantly more efficient than the brute force method. The two-pointer approach offers a clear advantage, as it is both efficient and avoids unnecessary computations. We also explored a third approach based on mathematical observations, specifically Fermat's theorem. This theorem states that a number can be expressed as the sum of two squares if and only if all prime factors of the form, for k plus 3, in its prime factorization have even exponents. The steps involve factorizing c and verifying this condition for all relevant prime factors. While mathematically elegant, this method has its drawbacks. Factorization itself has a worst-case complexity of O, sqrt, c, and implementing this approach in code can be challenging due to the complexity of prime factorization and mathematical reasoning involved. Given the constraints of the problem, this approach is less practical for programming purposes. Ultimately, we selected the optimized two-pointer approach for several reasons. It is clear and straightforward to implement, avoiding the need for advanced mathematical concepts. It achieves an optimal complexity of O, sqrt, c, making it efficient and scalable for large values of c. These factors make it the most suitable strategy for solving this problem. The key insight that makes the two-pointer approach so effective is its systematic exploration of valid pairs without redundancy. Geometrically, the problem can be interpreted as finding two integers whose squares add up to c. By adjusting the pointers based on whether the sum is less than, greater than, or equal to c, we eliminate the need for nested loops or exhaustive searches. This realization was the aha moment that made the solution both elegant and efficient. Comparing the two-pointer approach to the alternatives highlights its strengths. While the brute force method is simpler to conceptualize, it suffers from redundant calculations and higher computational overhead. On the other hand, the Fermat-based mathematical approach, though insightful, is less practical for implementation due to its reliance on integer factorization and advanced number theory. The two-pointer approach strikes the ideal balance between simplicity and efficiency. It avoids the pitfalls of brute force and the complexity of mathematical reasoning, making it the most practical choice for this problem. This balance is what makes the two-pointer approach the most effective and scalable solution for determining if a number can be expressed as the sum of two squares. To solve this problem, we need to determine if a non-negative integer, c, can be expressed as the sum of squares of two integers, a and b. In other words, we need to check if there exist integers such that a superscript 2 plus b superscript 2 equals c. The brute force approach involves understanding the equation itself. Since squares of integers are always non-negative, both a and b must also be non-negative. We can iterate over possible values of a and calculate the corresponding b by solving for b superscript 2 equals c a superscript 2. However, we must ensure that b superscript 2 is a valid square, meaning b must also be an integer. To optimize this process, we can set the range of a. Instead of iterating over all possible integers, a only needs to range from 0 to the square root of c, because if a superscript 2 exceeds c, b superscript 2 would become negative, which is not possible. Using this upper bound ensures efficient computation. For each value of a within this range, we compute b superscript 2 and check if it's valid. Once we compute b superscript 2 equals c a superscript 2, the next step is to check whether b is an integer. To do this, we verify if the square root of b superscript 2, or sqrt, c a superscript 2, is indeed an integer. In programming, this can be done by checking whether sqrt, c a superscript 2, has no fractional part, for example, by using the condition sqrt, c a superscript 2, %1 equals 0. If this condition is true, it means b is an integer, and we have a valid pair, a, b, such that a superscript 2 plus b superscript 2 equals c. If we find at least one such pair, we return true. If the loop completes and no valid pair is found, we return false. Key insights here include the optimization by limiting the range of a to sqrt, c, which reduces the number of iterations significantly for larger values of c. Additionally, the direct calculation of b eliminates the need to iterate through all possible values for b, further improving efficiency. By starting a from 0 and limiting it to sqrt, c, we ensure that the computed value of b superscript 2, which is c a superscript 2, is always non-negative. This eliminates the need for additional checks to avoid negative values of b superscript 2. The algorithm relies on simple variables, with a representing the first number being squared and b representing the square root of the computed value, c a superscript 2. No additional data structures are required since we only iterate and compute values. The time complexity of this approach is O, sqrt, c, as the loop runs from 0 to sqrt, c, and each iteration involves a constant time operation to compute sqrt, c as superscript 2. The space complexity is O, 1, as the algorithm only uses a few variables. Edge cases include c equals 0, where the only valid solution is a equals 0 and b equals 0, since 0 superscript 2 plus 0 superscript 2 equals 0. In the edge case where c equals 0, the algorithm correctly returns true because the only solution is a equals 0 and b equals 0, satisfying the equation 0 superscript 2 plus 0 superscript 2 equals 0. If c is a perfect square, the algorithm will find a solution where a equals sqrt, c, and b equals 0, or vice versa. For very large values of c, the algorithm remains efficient because it limits the loop to sqrt, c, iterations, ensuring feasibility even for large inputs. Another important consideration is prime numbers. Some prime numbers, such as 3, 7, or 11, cannot be expressed as the sum of two squares. The algorithm correctly handles these cases, returning false when no valid pair of integers is found. The provided pseudocode demonstrates the algorithm in action. It iterates over possible values of a, computes b superscript 2, checks if b is an integer, and returns true if a valid pair exists. Otherwise, it returns false after completing the range. To better understand the algorithm, let's walk through a couple of examples. First, consider the input c equals 5. Starting with a equals 0, we calculate b superscript 2 equals 5, 0 superscript 2, which equals 5. However, 5 is not a perfect square, so we move to a equals 1. Here, b superscript 2 equals 5, 1 superscript 2, which equals 4. Since 4 is a perfect square, b equals 2, and we return true because 1 superscript 2 plus 2 superscript 2 equals 5. Now consider c equals 3. With a equals 0, b superscript 2 equals 3, 0 superscript 2, which equals 3. Since 3 is not a perfect square, we proceed to a equals 1. This time, b superscript 2 equals 3, 1 superscript 2, which equals 2, and again, 2 is not a perfect square. Since no valid pair of integers satisfies the equation, we return false. This walkthrough highlights how the algorithm efficiently determines whether a number can be expressed as the sum of two squares by leveraging mathematical properties and minimizing unnecessary computations. This solution to LeetCode problem number 633, sum of square numbers, determines if a non-negative integer c can be expressed as the sum of squares of two integers. ###code walkthrough. 1. Imports. The math module is imported to use the sqrt function to calculate the integer square root of c. 2. Initialization. A two-pointer approach is used. Left starts at 0, the smallest possible value for one of the squares. Right starts at sqrt, c, the largest possible value for the other square. 3. While loop. The loop continues as long as left is less than or equal to right. The current _sum variable calculates the sum of the squares of left and right. 4. Conditions. If current _sum equals c, the function returns true because a ℏ2 plus b squared equals c has been satisfied. If current _sum is less than c, increment left to increase the sum. If current _sum is greater than c, decrement right to decrease the sum. 5. Return value. If no valid pair is found after the loop ends, the function returns false. ### complexity. Time complexity, O, sqrt, c, because the loop iterates at most from 0 to sqrt, c. Space complexity, O, 1, since only a few variables are used. This approach is efficient, leveraging the two-pointer technique to avoid unnecessary calculations and iterating only within the feasible range of values. This is the Java implementation of LeetCode problem number 633, sum of square numbers, which mirrors the logic of the provided Python solution. The solution uses two pointers, one starting from 0 and the other from the square root of the input c. The pointers evaluate all possible sums of two squares to determine if they equal c. Key differences in Java include explicit type declarations, the use of math.sqrt for the square root calculation, and the handling of large numbers with long to prevent integer overflow when squaring values. In this problem, we are tasked with determining whether a given non-negative integer, c, can be expressed as the sum of squares of two integers, a and b. In other words, we need to check if there exist integers such that a ℏ2 plus b squared equals c. To illustrate the solution, we'll consider three examples, starting with c equals 5. Here, we initialize two pointers, left starts at 0, and right is set to the integer square root of c, which is 2 in this case. In the first iteration, we compute the sum of the squares of these two values, left ℏ2 plus right ℏ2, which equals 4. Since this sum is less than c, we increment the left pointer to explore the next potential pair. In the second iteration, the sum of squares becomes exactly 5, which matches c. At this point, we return true, as we have successfully found two integers whose squares sum up to c. The output for the first example is true. Now, let's consider another example with c equals 3. Again, we use two pointers, left starts at 0, and right is set to the integer square root of c, which is 1. In the first iteration, we calculate the sum of squares, left caret 2 plus right caret 2, which equals 1. Since this is less than c, we increment left to 1, narrowing down the range of possible pairs. In the second iteration, the sum becomes 2, which is still less than c. So, we increment left again to explore further. At this point, we've exhausted all possible pairs where left is less than or equal to right. As left is now greater than right, the loop terminates, and we conclude that no valid pair of integers satisfies the condition a caret 2 plus b squared equals c for c equals 3. Therefore, we return false. Next, we move on to the third example with c equals 10. This time, the left pointer starts at 0, and right is initialized to the integer square root of c, which is 3. In the first iteration, the sum of squares, left caret 2 plus right caret 2, equals 9. Since this is less than c, we increment left to explore the next pair of integers. In the second iteration, the sum of squares, left caret 2 plus right caret 2, equals 10, which matches the value of c. As we found two integers whose squares sum up to c, we return true. Through these examples, we can observe a consistent pattern in how the two-pointer approach works. The left pointer starts at 0, while the right pointer begins at the integer square root of c, representing the largest possible integer to square. Depending on whether the current sum of squares is less than, equal to, or greater than c, we either increment left to increase the sum or decrement right to decrease it. By doing this systematically, we ensure that all valid combinations of squares are checked before the loop terminates. To analyze the efficiency of this algorithm, let's consider its time and space complexity. The time complexity is O(sqrt) c, as both pointers traverse at most sqrt c steps before the loop terminates. This makes the approach highly efficient for large values of c. The space complexity is O(1), as the algorithm uses only a constant amount of additional space for variables such as the pointers and intermediate computations. By leveraging the two-pointer technique, we've demonstrated how to efficiently determine whether a given non-negative integer can be expressed as the sum of squares of two integers. This approach is both intuitive and computationally optimal for the problem at hand. The time complexity of this solution is O(sqrt) c, where c is the input integer. This is because the algorithm uses a two-pointer approach, with the left pointer starting at 0 and the right pointer starting at the square root of c. Since the largest possible square root of any number c is sqrt c, the right pointer has a maximum initial value of sqrt c. The while loop continues as long as the left pointer is less than or equal to the right pointer. During each iteration, the algorithm calculates the sum of the squares of the left and right pointers and adjusts their positions depending on whether the sum is less than, greater than, or equal to the target c. The left pointer increments from 0 to sqrt c, while the right pointer decrements from sqrt c to 0. This means the total number of iterations is proportional to sqrt c. Furthermore, each iteration involves constant time operations like addition, multiplication, and comparison, which are O(1). When you combine these factors, the overall time complexity of the algorithm is O(sqrt c). The space complexity of this solution is O(1), meaning it uses constant space regardless of the input size. This is because the algorithm does not rely on any additional data structures, such as arrays, hash maps, or recursion stacks. Instead, it only uses a small number of variables, including two integers for the pointers, left and right, an integer for the current sum, and a floating point variable for the square root calculation. Since the number of variables does not grow with the input size c, the memory usage remains constant. As a result, the space complexity is independent of c and is classified as O(1). When comparing this approach to a brute force or naive solution, the efficiency of the two-pointer method becomes clear. A naive approach would involve iterating through all possible pairs of integers a and b such that a squared plus b squared equals c. This requires two nested loops. The outer loop iterates over A from 0 to sqrt, c, and the inner loop iterates over B from 0 to sqrt, c. The resulting time complexity is O, sqrt, c, asterisk sqrt, c, which simplifies to O, c. In contrast, the two-pointer approach significantly reduces the search space. By exploiting the sorted nature of squares and dynamically adjusting the pointers based on the sum, the algorithm avoids exploring all possible pairs and instead focuses on a single pass through the range from 0 to sqrt, c. This optimization brings the time complexity down to O, sqrt, c, making it far more efficient than the naive method. The algorithm's performance can also be analyzed in terms of best, average, and worst-case scenarios. In the best case, the algorithm finds a valid pair of integers a and b that satisfy the condition a squared plus b squared equals c within the first few iterations. For example, if c equals 5, the pair 1 and 2 satisfies the condition early, and the loop exits quickly. While the time complexity remains O, sqrt, c, the actual number of iterations is minimal. In the average case, the algorithm performs a number of iterations proportional to sqrt, c, before either finding a valid pair or exhausting the range. The time complexity in such cases is still O, sqrt, c. In the worst case, when no valid pair exists, such as when c equals 3, the algorithm iterates through the entire range from 0 to sqrt, c. Even in this scenario, the time complexity remains O, sqrt, c, as it is upper bounded by the maximum size of the range. The space complexity remains constant across all cases because the algorithm does not use any additional memory. This makes the solution both time efficient and space efficient, with a time complexity of O, sqrt, c, and a space complexity of O, 1. When working on this problem, there are a few common mistakes to watch out for. First, not handling edge cases properly can lead to incorrect solutions. For instance, if c equals 0, both a and b can be 0, while for c equals 1, valid pairs include e equals 1, b equals 0, or e equals 0, b equals 1. It's important to explicitly test these scenarios to ensure your solution handles small inputs correctly. Another mistake is using inefficient brute force loops. A naive approach might explore all combinations of a and b, even when a or b exceed the square root of c, resulting in unnecessary computations. Instead, you can limit your search space to values up to sqrt, c. Lastly, some solutions incorrectly check for integer solutions. For example, when calculating b equals sqrt, c s squared, it's essential to verify whether b is an integer. Failure to do so could lead to false positives. You can fix this by using a condition like b.is underscore integer, or explicitly checking if int b equals b. Another common issue is ignoring symmetry in pairings. Since the order of a and b doesn't matter, treating a, b, and b, a as separate pairs can introduce redundancy or errors, particularly when unique pairs are required. To address this, you can enforce constraints like a equals b while iterating. Additionally, floating point precision errors can arise when using operations like math.sqrt, especially for large values of c. These errors might lead to slight inaccuracies in the computed values. To avoid this, use integer arithmetic wherever possible or validate results carefully after performing floating point calculations. By addressing these issues, your solution becomes not only more efficient but also more robust. A key insight for solving this problem is recognizing that it can be reduced to iterating over possible values of a from 0 to sqrt, c, and checking whether c a2 is a perfect square. This drastically reduces the complexity compared to a naive brute force approach. Additionally, the problem has connections to Pythagorean triples and modular arithmetic. For example, certain values of c, such as those where c is identical to 3 mod 4, cannot be expressed as the sum of two squares. Leveraging such mathematical patterns can help optimize your solution. Once you calculate a2, the only remaining task is checking if c a2 is a perfect square, which avoids redundant calculations. During an interview, it's also helpful to communicate trade-offs clearly. For instance, you could discuss the advantages of a mathematical approach compared to iterating through all possible pairs, showcasing your ability to evaluate different strategies effectively. This problem is closely related to a few other challenges on LeetCode. For instance, LeetCode 367 asks you to determine if a number is a perfect square, while LeetCode 279 focuses on finding the minimum number of perfect squares that sum to a given n. Another related problem, LeetCode 204, involves counting prime numbers, which also employs an optimization strategy that limits the search space, often up to sqrt, n. As for alternative approaches, one efficient method is the two-pointer approach. Here, you initialize one pointer at 0, representing A, and another at sqrt, C, representing B. By adjusting the pointers based on whether a (2 plus b(2) is less than, equal to, or greater than C, you can narrow down the search space efficiently. This method has a complexity of O, sqrt, C, and is faster than brute force, though it requires careful pointer manipulation. Another approach involves mathematical modular checks, where you use number theory to quickly rule out impossible cases, such as when C is identical to 3, mod 4. While this method is highly efficient for certain scenarios, it requires deeper mathematical knowledge and may be less intuitive for some. Finally, there's the brute force approach, which is the simplest to implement but also the least efficient. In this method, you iterate through all possible pairs of A and B such that a(2 plus b squared equals C. While this approach has a worst-case complexity of O, C, it can be useful for testing or for smaller values of C. However, for larger inputs, it quickly becomes impractical due to the sheer number of computations required. Despite its inefficiency, brute force can serve as a baseline solution, helping you verify the correctness of more optimized approaches. By understanding its trade-offs, you can better appreciate the need for more advanced techniques like limiting the search space or utilizing mathematical insights. Great job! To recap, we explored the problem of determining whether a number can be expressed as the sum of two squares. We reviewed an efficient algorithm with optimal time and space complexity. Remember to practice similar problems to strengthen your understanding. Thanks for watching, and don't forget to like and subscribe for more content. See you in the next one. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!